Hello everyone, welcome back to the channel. In this video, I'll be looking at questions 5.11 to 5.20. So take a second, pause the video and read the question. So if you've read the question, you can see that whatever they are talking about from here up to this point, they are talking about the relationship between what? The stress, the fracture stress and the fracture toughness. So that's what they are talking about over here. But when the question actually starts is here, where it says you use the K1C and Young's modulus chart. That means this figure right next to it to identify the class of material. So not a single material. They're telling you to identify the class of material with K1C greater than 1, K1C greater than 1, and high values of what? K1C over E values. So first, we are looking for what? K1C values greater than 1. So if you go to the chart, you can look at the chart here. So we are looking for values what? Greater than what? 1. So this is 1, and we're looking for what? Values greater than 1. Then we are looking for materials with what? High K1C over E values. So this is K1C. This one here is what? K1C squared over E. Then this is the one that we're looking for what? K1C over E. So if you're trying to find high values of what? This line, any material here has what? High values of what? K1C over E. Then any material that is below this line have what? Low values of K1C over E. So if you're trying to what? Minimize this line. If you're trying to minimize this line, then all the materials here will be best. But if you're trying to what? Maximize this line, all the materials here will be best. So in this question, we're looking for what? High values of what? K1C over E. So we are looking for all materials what? Above the line. So in order to find our material with the high K1C over E, all we have to do is what? Move this line all the way back down here, and the first class of material that is above the line is our best class of material. So first, let us draw the line for what? 1 MPa times meter raised to power 1 over 2. So let's draw our first line. So we are looking for what? 1 MPa. So we'll go exactly at 1 MPa. We leave our ruler at 1 MPa. Then once we leave our ruler at what? 1 MPa, exactly at 1 MPa, we can now draw a line for 1 MPa. So once we draw a line for 1 MPa, we know that all the materials here have what? Lower than what? 1 MPa. Then also we need to trace this line for K1C over E. We'll get our ruler again. Then make sure that we place it exactly at what? K1C over E. That's the line that we are looking for at what? K1C over E. Once we have it, once we have our line that is placed perfectly at K1C over E, we can see that everything here is placed at K1C over E. All we have to do is what? Translate this line all the way down. So as we are going down and we are going down, you can see the first class of material have passed. Now we have to what? Draw a line. We can now draw a line. Now we have this. We can now draw a line. Now that we have our line, we can say that every material below here has what? Lower K1C over E. So we are looking for materials with both higher what? K1C values. So every material here and every material what? Here. So all the class of material that we have here is what? This which is what? Polymers and elastomers. So these are material that passed our selection. So our answer here is what? Polymers and elastomers. So this is our answer to this question. Let's move on to the next one. Okay, for this question, this is like the first question that we solved, like question 5.11. So take a second, pause the video and read the question. So if you read the question, you can see that everything they are talking about here, everything here is just talking about what? Relationships between pressure, K1C, and this value M. So where the question starts is here. So here they said use the K1C and fracture stress chart, which is this chart that we have here, to identify 3 alloys that have what? High values of what? M. And what's the formula for M? The formula for M is what? K1C squared over what? Yield strength. So this is the chart that we are looking for. And we are looking for what? K1C squared over what? Stress. So this is the line that we are trying to use to find our material. So everything here what? Will have what? Higher K1C squared over K1C squared over stress value, and everything here will have what? Lower K1C squared over what? Stress value. So all we have to do is what? Get our ruler. Once we get our ruler, we now place it exactly at this line, right? We just place it exactly at this line. So once we have it at this line, now what we have to do is what? Move it down. So as we are moving it down, all the materials that pass, the first material that passes is the one that have what? Highest K1C squared over what? K1C squared over what? Stress value. So as we go all the way down here, they said what? Identify what? Three alloys. So we are looking for what? Metals. So once we get here, we can see we have candidates that have already passed. So if you come here, you can see, let's just draw a line first, so it's going to be easy for us. So once we draw a line, we'll get rid of the ruler. Then we can see the materials that passed here. You can see what? Copper alloys. You can see another one, nickel alloys, and we can see what? Steels. So these are the three alloys that pass. You can also see what? Low alloy steel. You can classify any of them, pick any of three of them as your best material. Low alloys, stainless steel, nickel alloys, and what? Copper alloys. So that's your best material for this selection. Let's move over to what? Question 13. Okay guys, take a second, pause the video and read the question. So if you've read the question, you can see that where the question actually starts is here, where they're telling you to use these charts, K1C and fracture stress charts, to identify three materials with what? K1C values greater than what? 30 MPa. And also the materials with what? Highest possible strength. So they didn't give us a value of what? Strength, but they gave us the value of what? K1C. So for the K1C, they say let us find materials with what? Greater than 30. So this is our 30 over here, and we are looking for the highest possible strength. We can say 1000, greater than what? 1000 MPa as our strength. All we have to do is what? Get our ruler, place it at what? 30 MPa. Once you place it at 30 MPa, you draw your line. That's for the fracture toughness. Then for the stress, you bend your ruler all the way towards 90 degrees. Then you come all the way towards 100. They just say just below 100, just below what? 1000, sorry. So you draw your line for 1000. Once you draw your line, take off your ruler. You're looking for what? Everything down here did not pass, and everything this side did not pass. You're looking for what? Materials with what? Very high fracture toughness and what? Very high what? Strength. So based on this, you can see the materials that passed are, if you see here, you can see what? Carbon steels. So this is 1. You can see what? Titanium alloys. This is 2. Titanium alloys, carbon steels, and we still have one more material. You can see here there is small part of this line, this big bubble. You can see the small part of this big bubble over here. And which material is this? Which is what? Nickel alloys. So we have three materials, which are what? Nickel alloys. The next one is what? Carbon steels. And the last one what? Is what? Titanium alloys. But the question did not end there. The question says, now use the cost chart. So use the cost chart in figure what? 4.9 to rank these three materials based on what? The cost of these three materials. So we have three materials: nickel alloys, carbon steel, and what? Titanium alloys. So we are looking for what? The chart, figure 4.9. So we have what? Figure 4.9 here, and we are looking for what? Three materials, and we are looking to rank each of these three materials. So if you look at this chart here, these are what? Titanium alloys. And where is our carbon steel? These are carbon steel. And if you look closely, they didn't what? Label what? Nickel alloys in this chart. But based on the shape of the bubble that we've got in the last one, this should be your what? Nickel what? Alloy. So based on this, you can now rank these three materials. That number one that is best for this selection is what? Based on the cheapest, as the cheapest material is what? Carbon steels. So carbon steels. Then number two is what? Nickel alloys. Then the costliest is what? Titanium alloys. So this is it for this question. Let's move on to what? 5.14. Okay guys, for question 5.14, here they are telling us to find materials that should make what? Good bells. We are looking for materials that we can use to make what? Good bells. That's what we are looking for in this question. So based on that, the function that we need is what? Low what? Damping, or low damping coefficient, which is this loss coefficient. We're looking for the lowest values of what? Damping. So any material with low damping will make what? More noise. Then any material with what? High damping will have what? A dead sound, which is what said in the question. Will have a dead sound, like mostly with, think of what? Polymeric materials or foams. Those materials will make a dead sound if they have what? High damping. So we are looking for materials with what? Low damping, right? So if you come here, we're just looking for the best materials for bells, the best based on what? These charts that we have over here. So if you're looking at this chart, we're looking for what? The lowest what? loss coefficient. So if you come here, definitely it should be somewhere around here. So number one material we can see here is what? Silica glass. Another material you can see here is what? Si3 sodium nitride. Another material is what? Silicon carbide. So this is silicon nitride and silicon carbide. We can also see tungsten carbide. We can also see what? Alumina, Al2O3. You can also see what? Soda glass. We can also see what? Copper alloys. So once you have all this selection, you can now go further in documentation and read about what? These materials, to know which of these materials have what? Traditionally been used for what? Bells. So if you look closely, you can see that what? Copper alloys are the materials that have been used for traditionally for bells, usually what? Brass and what? Bronzes. So this is our best selection for this material. But also you know that what? Silica glass is also what? A good material for bells. Silica glass or alumina or any of these materials is good for the answer of this question. Any of this material what? Has what? Low damping. But traditionally you can see that copper alloys are the best material for what? For bell production. So this is your answer for this question. Let's move on to the next one. So for question 15, this is an easy question as well. So they're telling us to use this chart to find metals, only metals that have what? The highest possible damping. So metals that have what? Highest possible damping. So if you come to this chart, any material with what? High loss coefficient has what? High possible damping. So we're looking for the family of metals. So these are metals. I'm looking for what? High values of what? Loss coefficient. So first material that we have what? Is what? Lead alloys. So these are first material. So everything here is concrete, brick. So they fall under what? Composite materials, right? Then we have what? Magnesium alloys, which is this one. The next highest one should be this one, this tall one, and I think it's what? If you look at the chart closely, it has to be what? Aluminum alloys, I guess. So these are the three best what? Metals that have what? Highest possible what? Damping. So the best materials that you have is what? Lead alloys and what? Magnesium alloys. Then you can what? Add what? Aluminum what? Alloys. So that's it for this question. Let's move on to the next one. So guys, for question 5.16, this is a straightforward question as well. So they are telling us to find what? Three materials with what? High thermal conductivity, so good conductor of heat, and high electrical resistivity. That means poor conductor of what? Electricity. So here, if you look at this chart, we are trying to what? Maximize what? Thermal conductivity, and we are trying to what? Maximize what? Electrical what? Resistivity. So if you want to maximize these two functions, you can see that any material that is in this box is the best material. But since there are no other material, we can move this what? One step. So if you move it down the next step, any material within this next box is the what? The best material. So once you are in this box now, you can know that any material within this is the best material. So right now, since we already have three materials, anything here and here. So the first material is what? Aluminum nitride. Second one is what? Alumina. And the third material is what? Silicon nitride. So these are our three best material for this question. So let's move on to the next one. Okay, for question 5.17, take a second, pause the video to read the question. Okay, if you've read the question, they're looking for a material used to make a window where beams can pass through. So for beams to pass through, the material has to be what? Transparent. The material has to be transparent, one. So that's one of the criteria. The material has to be transparent. So the next thing it says, there is a problem when beams are passing through. The material tries to what? Absorb what? The heat. And you don't want the material to what? Absorb heat. That's why you want the material to have what? A high thermal conductivity. So a high thermal conductivity. Also, you want a material that will not expand once it is conducting heat. You don't want it to what? Expand. So you have what? Low expansion. So this is what you want, low expansion. So these two things are given by the formula, this M, where M is equals to what? The thermal conductivity divided by thermal expansion. So the higher the value of M, the better the material. So that's the material that we're looking for, the material with the highest what? Value of M, that has what? High thermal conductivity and low thermal expansion. But first, the first criteria is the material has to be what? Transparent. It has to be what? Transparent to light. So if you are looking at our chart here, you can look at materials that are transparent. First, polymers and elastomers has to be cancelled, because there is no material over here in polymers, even what? Natural materials. If you look at natural materials, unless there is diamond in this chart as natural materials, since there is no diamond, you have to what? Cancel out this. Sometimes epoxy in a way can be transparent in some way, in some kind of coating epoxy, but it is not very transparent for the application that we are looking for. So if you come to composites over here, also metals has to be cancelled off. Technical ceramics, the only technical ceramics you can see that can be transparent is alumina. Is the only technical ceramic that we can see. So every other ceramic we have to cancel it off. So we only have one material yet. So if you look at composite, the only composite that you can see here, you can see glass material, which is soda lime glass. Then the next material you can see over here is silica glass. So we have 3 materials competing to be the best material for this high power laser window. So we have 3 materials. So in order to find the best material, we have to calculate the value of M for each of these material. So first we have alumina, Al2O3, and we are looking for lambda divided by alpha. That's what we are looking for. The second material is the second material we have is silica glass. So we look for silica glass, which is equals to, we'll now find our lambda over alpha. Then the last material we have is The last material we have is soda lime glass or soda glass. So we have soda glass. So all we have to do is calculate M for each of these material. In order to make our life easy, we can either calculate for the higher limit or the upper limit, the higher limit or the lower limit. So first, we can just use the higher limit of each of these properties. So first for thermal expansion. So this is thermal expansion. We want to make this value so low. So we are looking for the thermal expansion for these 3 materials. So first for alumina. So this is alumina. Let me just circle alumina so it can be easy. So this is alumina. We are looking for the highest value of thermal expansion that this material can give. So if you put it here, so this is 10. So if you look at here, this is 10. So above 10 is just above 10. So you can call that 10.2. Sorry. So since it's above 10, we are looking for this over 10.2. Also, you can see that thermal expansion is in microns. So times 10 raised to power minus 6. So that's the thermal expansion. Also, let's go to the next one. The next material is soda lime glass as well. For soda lime glass, this is 1, this is 2, this is 3, and this is 4. This is 4. So it's just above. So for soda lime glass, it's just above 4. So this is 3 and this is 4. So it's just above 4. So you can call it 4.2 for soda lime glass. So you can say for soda lime glass we have 4.2 soda lime glass. So come here, write 4.2 times 10 raised to the power minus 6. Then for silica glass, you can place your value for silica glass. So if you come here, this is 1. So this is here just exactly, if you raise it up exactly, let's say 0.9. For silica glass we have 0.9 times 10 raised to the power minus 6. Then is now we have to find the thermal conductivity of each of these materials. So we place our ruler vertically. So we come here, I'll place our ruler. So if you look at this ruler, this is 10, this is 20, this is 30, this is 30, and this is around 40. And this is around 40, but it's not exactly at 40, just before 40. So we can say it's 38 for alumina. Then for soda lime glass or for silica glass, we come here for silica glass. If you place this here for silica glass, you can see this is 1. So you can call this for silica glass. You can call this like 1.7, something around that nature. So 1.7, we call this 1.7 for silica glass. Then for soda glass, if you place this for soda glass, so this is the soda glass that we're looking for. So for soda glass, if you place this in soda glass, just near soda glass, so this is 1. So for soda glass, you can see it's not really half of soda glass, but it's almost at the center. So you can call this 1.4. So if you try and calculate this, I get my calculator and try to punch out all of these numbers. We can have this first one, remove our ruler. You can have this first one as the value of this first one. If you punch it out, it will be 3.72 times 10 raised to the power 6 W over M. So if you punch out this second one to give you 1.89 times 10 raised to the power 6 W over M. Then if you punch out the last one to have what? 0.3 times 10 raised to the power 6 W over M. So based on this material, the best material for this selection is what? Alumina. So after alumina, our second best material is what? Silica glass, and our last material is what? Soda lime glass. So now let's move on to the next question. Okay, for this question, we are looking for materials. If you can take a second to look at the question, but here we are just looking for polymers. So here it says polymers that can be used above what? 200 degrees C. So all we have to do is just draw a line at 200 degrees C. So get our ruler, place it exactly at what? 200 degrees C. Make sure we are at 200 degrees C. Then we can draw a line. So once you have your line, you can now find polymer. So this is the circle for polymer. So this is the family of polymers. This is polymers, and this is the family that we are looking for. So this is the family of polymers that we are looking for, just around here. So if you can see, the only polymers that have what? The maximum service temperature that is above 200 degrees C is what? If you look at here, you have what? Silicon elastomers, and the next one is PTFE, which is polytetrafluoroethylene, which is the two materials that we have, which is what? Silicon elastomers and PTFE. So those are our two materials for our what? Selection. Let's move on to. So guys, for this question, so if you can see, there are two parts to this question. A, they're telling us to use this first chart to find cheapest materials with a Young's modulus of greater than what? 100 gigapascal. So we are looking for materials with greater than 100 gigapascal and are the cheapest. So this is cheap. So we take our ruler, we place it at 100 gigapascal, place it at here, then we just put it at, it's already at 100 gigapascal. We'll now draw a line. So once we have a line, we can now look for cheap materials. So cheap materials means the lower, we want to what? Reduce what? Cost. So if you come here, the lowest materials that we have here is one. The cheapest material we have one is what? Cast irons, and the second cheapest material is what? Steel. So these are two materials for selection. So for A, these are our best materials for A. Then for B, they told us to use the next chart to find cheapest materials with strength above what? 100 MPa. So we'll go to chart B. So for B, we are looking for cheapest materials with what? Greater than what? 100 MPa. So we take our ruler as well. We'll bring out our ruler. Then we are looking for what? 100 MPa as well. So once we have it at 100 MPa, we'll now draw a line. Take out our ruler, then look for very cheap material. So the cheapest material, you look at the materials above this. So everything here is not selected. The materials above this, the cheapest material are what? Cast iron. Then if you're moving this way, you can see what? Carbon steels as another cheapest material. So the next one you can as well see is what? Aluminum alloys as one of the cheapest materials. So this is our selection for B. So this is our selection for B. So this is it for this question. Let's move on to the last question for this series. Okay, so guys, for the last question, this is a very easy question as well. It's telling us to find two materials with the lowest coefficient of friction. So based just by looking at the chart, this is coefficient of friction. The two materials with the lowest coefficient of friction is what? PTFE, which is what? Polytetrafluoroethylene, and the next one is what? Polyethylene. So these are our two best materials for this question. Okay, for the next question or the next series, we're going to be looking at chapter 5. So all the questions in chapter 5, which are 6.1 to I think 6.20. So thank you guys for watching. See